Hey there, everybody. This is Christian Horner, and we're going to go through some things that will help you, hopefully, with any final exams that you have in terms of AP Physics 1. So to get started, I think what we're going to do is just go through some problems, just kind of make sure that everybody kind of understands some of the basics, but more importantly, just make sure that I think everybody is comfortable with what you need to do to be successful on these. So we will take a look at these things and make sure that everybody's good. I've got a little issue here that I'm taking care of. So as soon as I can get this thing to work, we will get started. All right, so, okay, I think I have it now. I had a script that didn't work. And so let's get this going here. I'm going to pull up, hopefully, you'll be able to see my screen here in just a second. But I think I'm having a little issue with a script that's blocking some things. So we will try this one here. All right, let's see if this works. So sorry about this. All right, so here we go. Okay, so I think I've got it so that it works. Let's try one more thing here. I'm so sorry. It's working earlier, and now I'm having a couple issues. All right, so, okay, bear with me here for just a second, and we will get you on and get you some things that will help you as we go. All right, I think, yes, good. Okay, here we go. Now I think I have it. Bingo. All right, you should be able to see my screen now, and you can. That is awesome. All right, so let's go through some things without any more delay. Like I said, this is the AP Physics 1 Semester 1 review. Notice that down in the bottom, you will see there is a, let's just make sure that you can hear me too. So if you can hear me, just go ahead and type in the box, hello, so that I know that you can hear me. So I see Jack, Alvin. Oh, good. Okay, cool. All right, cool. So as long as you can hear me, we are going to be good. So let's go ahead and take a look at this review. This is for semester 1. So typically the things that we look at when we go through semester 1 are just graphing and relationships. And those typically can cover any of the topics that you go through AP Physics 1 in. But more specifically, we're going to look at graphing, and then we're going to take a look at kinematics. We're going to look at dynamics, so that's the study of forces. We are also going to look at kinematics, dynamics. We're going to look at energy a little bit, and we will also take a look at momentum, so some of the conservation laws. And I think those are the ones that are probably the most important, really, to go through and do. So first thing with graphing, I know I read the AP test every year, and I can tell you some of the things that we encounter when we watch students graph. The first thing that you'll want to do is make sure you understand the difference between a plot, so PLOT, versus a sketch. So if they wanted me to sketch a graph of this data, I wouldn't have to actually plot it. So all I would have to do is just go through and really draw whatever it seems to be telling me. So here I've got position in meters on the y-axis, and then I have time, and that is in seconds on the x-axis. And when I look at this, I see this goes from 0 to 1 to 2 to 3 to 4, so that's pretty easy to do. 5, 10, 15, 20. Okay, so I know this is a linear relationship. So I would draw a sketch of that. And really, that's all you would need to do. But this one's different. This one is actually going to be a plot. So we're not going to sketch. Instead, we're going to actually physically plot everything that you see here. So one of the things that you can do is you can abbreviate sometimes, but you don't want to do that unless it's absolutely necessary. So one of the things that I'm going to do here is, instead of putting X for meters, I'm going to go ahead and write out the word position. Notice I didn't put distance here. So this is really position. one of the big things that you'll see is distance is actually the change in position. So when you think about distance, you need to think about the change in position from the starting point to the stopping point. So in kinematics, there's two things that we can talk about. One of them is distance and the other one is displacement. So if I go straight from here to here, so this is my original position, this is my final, this would be my displacement. The distance would be the path length that I take. So for example, if I go along this curved path, if I measure the path and I find out that it is let's say it's 5 kilometers along the path, that would be a distance. The displacement is from where I start to where I finish. And so this would be my displacement. So distance is along the path. Displacement is as the crow flies, is sometimes what they say, or it's just from point A to point B, or from your original to your final. So position is different. Position is where you are at a particular time. And that's really what we're plotting here. So I'm going to start by looking at what is on each one of my axes. Time is on my x-axis. So in a lot of spreadsheets that students use, you'll notice that x is your x variables in the first column, and then the second column is your y variable. So let's go ahead. We're going to put time on the x-axis. So I'm going to start with 0, and then I'm going to see I've got 1, 2, 3, 4, 5, 6 different lines here, but I only go up to 4. So I'm actually going to go 1, 2, 3, 4, 5, 6. So I want to make sure I space this out well enough, and we're going to talk about how you can get the maximum number of points on the AP test. To do that, we've got to make sure that we have everything spaced out really well. So the scale of this graph is super important. We're going to start with a position of 5, and notice that I do not need to start at 0 on either of my axes. I did on this one, but I'm not going to on this one. I want to fill up as much of the graph as possible, so I'm going to start the y-axis at this mark at 5, and that's 100% okay. If you want to double check this, go ahead and take a look at any of the 5 AP tests that have come out, the 15, 16, 17, 18, or 19. And you'll see graphs that look just like this. They've got these bold boxes, and then they've got these dotted lines on the inside. Each one of these dotted lines refers to 2, 4, 6, 8. So this would be 0.2, 0.4, 0.6, and 0.8. So that's what they refer to. So this is 15, then we have 20. I'm going to put 25 here and 30. So let's go ahead and plot everything that we have. So to plot this, we're going to start with 0 and 5. So I'm going to put a dot right there. You want to make your dots big enough that they can be seen, but not so big that they're taking up a lot of space. 1 and 10. So here we go. There's 1 and 10. Then I'm going to do 2 and 15. I'm going to do 3 and 20. And then I'm going to do 4 and 25. So now I have my plotted points. I also have my axes, and I have the proper labels on each one. This one I probably should write time, so I'm going to do that. Next thing I'm going to do is draw a straight line. And I will tell you on the AP test, we're very particular about straight lines. If you halfway do this and you kind of do it and it kind of looks like this, then you're not going to get any points. And the reason you don't get a point for this best fit line is it's not a best fit line. It's not even straight. So what I'm going to do is I'm going to erase it. I'm going to tell you absolutely, positively, 100%, you want to make sure you always have a ruler anytime you take a test. It is allowed on the AP Physics 1 exam or the AP Physics 2 or the AP Physics C. So please, please, please make sure that you are allowed a ruler. Let your teacher know, have them look it up in the course and exam description guide. And you can have a ruler or a straight edge, just as long as there's nothing written on the straight edge, no formulas or equations or sample problems. So now if I go through and I actually use a ruler to do this, I should be able to get a very nice straight line. If you extend it past that, that's absolutely fine as long as you follow that straight line. But the only thing we look at when we grade this is we look to see where your dots are. There are, if we count, you're going to see there's 1, 2, 3, 4, 5, 6 boxes to the left or right, and 1, 2, 3, 4, 5 up. So there are 30 total boxes. We want you to fill up half of those boxes at least. So you need to fill up 15 boxes. So you look at this and I'll tell you it's okay, but you'll say, no, wait a minute, it's not. It doesn't fill up 15 boxes. Actually, it does. When we count the boxes, we're going to start where your first dot is. And this first dot is adjacent to this box. So this is box number 1. Then we have another one. So that's box 2, 3, 4. And then this dot is just right on that line. So we're going to go ahead and count it over here. So that's 5 boxes to the left. Then we're going to count up. So this is 1, 2, 3, 4. And then this dot, we can either call it this box up here or we can say it's down here. Either way, you're going to be set because 5 boxes across by 4 boxes up is 20 boxes. And because you filled up those 20 boxes, that is an AP Physics 1 point. So you get 1 point for what we call scale. We want to make sure that you filled up 15 of those 30 boxes. You also get 1 point for having both of the proper and correct titles with units. So your axes, titles, and units, that is a point. You typically get a point for plotting your points and then drawing the best fit line. And let's say that my points weren't so perfect. Instead, let's say that I had 1 point. Oops, let's go back to red. Here we go. Let's say I had 1 point here and 1 here and 1 up here and 1 down here. I've gone through, if you look at those new points, I still have a best fit line because I have the same number of points above as I do below the line. So as long as you've done that as you go through, then that would be perfect. And that is what you want. So your best fit line is a point, and then your plotted points, as long as you have them in the right place, is a point. So let's count up how many points we have all together. So this is going to be 1, 2, 3, 3 points so far, plus we had our straight line point or our best fit line point. So that's 5. So 1 for the dots, 1 for the scale, 1 for labeling and having the correct axes, labels, and units, and then 1 for our best fit line. All right, so that's just a little review of graphing and some things that are super important in terms of graphing, just general graphing things. In kinematics, graphing is used a lot of the time, and there's 2 things you have to recognize when you do a kinematics graph. Most of the time, you're going to end up with something where you have position. So position, and that's in meters. And then you will have time, and that is in seconds. So let's say that we end up with a position time graph that looks a lot like this. So we've got, I'm just going to draw the line here. So we've got a straight line across. Now, if you see a graph like this, what they're going to do is they may or may not have some numbers here. They might just say like 0, 2, and 4, and then this is 0, 2, and 4. And they'll ask you questions. So they want you to be able to analyze these graphs. And typically what they'll do is they'll ask you what is the velocity and what is the acceleration of these objects. So for position and time, we know that velocity is equal to the change in position over the change in time. And here my change in position is 0. So I know that the velocity of this object is 0. If the velocity of the object is 0, we know that our acceleration is also 0 at this point because this is a very flat line. So there's no change in velocity and no change in position either. So that's one graph that you're going to end up seeing is it's going to just have that very, very straight line, okay? Just a horizontal line. And that tells me that it doesn't have any speed. It's just sitting still. You're going to get another one, and it might look a lot like this. And they will ask you again, what is the velocity and what is the acceleration? So when I look at this, I need to find out if I have position and time, what is the slope of my best fit line? So here, velocity is change in position over change in time, or sometimes you'll see it's distance over time, and they're getting that from the change in position. So really, change in position is critical here. I've got 4 minus 0 over 4 minus 0, so that gives me 1 meter per second. And there's no change in speed since the speed is constant, so this is also 0 meters per second. The last type of position versus time graph that you're going to probably see as a review is one that has more of a curve. So let's say that you see one that looks like this. So this is a parabola, and a parabola means that we have an accelerating graph. Now, how do I know that this object is accelerating? Remember the slope at any tangent point. So right at a half second, I see that this is my slope. So that's my velocity. But then I'm going to move over here and I'm going to draw another tangent line. And this has a steeper slope. So our velocity is going up. And then over here, I have an even steeper slope. So now my velocity is really rising. So I could find these three velocities. If I found the initial velocity, the final velocity, any of the two velocities, I could also then find the acceleration. There's a better way to find acceleration though, and that's to take our position versus time data and change it. So this is what we call to linearize a curved graph. So this is a parabola as a quadratic relationship. And if I want to make it so that I get a straight line and I can find out what acceleration is, I need to plot my y thing versus whatever I have on the x-axis, but I have to square it. So what I'm going to do is I'm going to go through and try to do that with this. Right now I see that I have 0, 0 point. This is 2, comma 1. Okay, so I have 2 and I have 1. And then over here, we've got about 3 on our x-axis. And we've got 1.6. Okay, and then I have 4 and 3. So this is going to be 4. And it looks like we have about 3 there. So these are times, and these are our positions. And I need to square my times. So instead of 2, I'm going to have 4. Instead of 3, I'm going to have 9. And then this is going to be 16. So we're going to change this a little bit and see if we can find out what the acceleration of this thing is. So I'm going to get rid of the numbers that I have here. I'm going to put new numbers in. And it looks like I need to go for time squared. I'm going to have 4, 9, and 16. So let's do this. Let's go over and we're going to put 4. 4 times 2 is 8. 4 times 3 is 12. And then 4 times 4 is 16. So I'm still filling up as much of the graph as I need. This is now time squared and second squared. Now I'm going to plot these points. So I want to go on the x, I'm going to go up to 1. So here's 1 right here. And I see at 1, I need 4. So I'm going to put that dot there. So I can get rid of this one right here. Then for my x, my position again, I have 1.6. So this is 1.6. And so I'm going to put this one about right here. Oops, move it down a little bit. And then finally at 16, it looks like it's about 3. And what's cool about this is, notice now we have a very straight line. So since I have a straight line and I have position versus time squared, so let's make these like this, we can go through and we can find out what the acceleration of this is. So now we have to think about our kinematics equations. And remember, there are 3 kinematics equations that you really need to know. You don't need to memorize anything on the AP test. Instead, you can use the equation sheet. So one of those equations is the final velocity is equal to the original velocity plus acceleration times time. The second one is the change in position is equal to the original velocity times time plus 1/2 of the acceleration times time squared. And then our last equation is the final velocity squared is equal to the original velocity squared plus 2 times the acceleration times that change in position. So when I look at my graph, I notice I have position and I have time squared. So out of all these equations, the one that has position and time squared is this one in the middle. And that's super important. Here's why it's so important. Let's find the slope of this line. So we've got 3 minus, and then this is 1. And we're going to divide that by 16 minus 4. So 16 minus 4. So 3 minus 1 is 2. And 16 minus 4 is 12. So that would be 1/6. And typically on the AP test, we really want to make sure that you have, instead of fractions, you will want decimal equivalents. So the decimal equivalent of this is 0.17. And now I know the slope. Our units for the slope are a meter per second squared. So everybody goes, yay, we found acceleration. But the problem is we really didn't. If you look at this equation, you're going to find out that if I write a physics equation for this, this is going to be the change in position is equal to, and notice how this goes through 0. This is our b value. So VOT is our b value, but it is 0 because this goes right through the axis. So here we go. So we're going to put a 0 plus, now our slope was 0.17, but we're going to put that half in here because in the equation we see that. So it's a half of 0.17 times time squared. So if I want to know what the actual acceleration is, I need to multiply the 0.17 times 2 because I want to multiply this whole thing by 2 to get rid of the half. So my acceleration here is the slope, and it's really 0.34 meters per second squared. So it's important that you see in a position versus time squared graph, the acceleration, whatever your slope is, so my slope is 0.17, I have to multiply that by 2 in order to get the true acceleration for that graph. All right, so that's probably enough of kinematics graphing. Let's go ahead and take a look at what you might experience on a dynamics graph. So we're going to move this so that maybe we can get the graph to come up. Okay, here we go. So typically, if you think about dynamics, the biggest equation that you can think of is force is equal to mass times acceleration. Now, on the AP Physics equation sheet, this is not shown, and it's because it really doesn't exist. We always want to know what are the sum of the forces, and the sum of the forces are the things that make things accelerate. So we're going to put acceleration is equal to the sum of the forces, and sometimes they'll put F net force, and we divide both of these by mass. So there's two ways to think about a graph and what happens when they want you to either analyze or draw or sketch a graph. And for this first one, we can say sum of the forces is equal to mass times acceleration. And let's say that we plot force, and remember force is in newtons here, and let's say that we put acceleration in meters per second squared down on the bottom. If I have a straight line, okay, so I'm just going to sketch this, I want to know what in the world does my slope represent? So this is where you get to be a little bit more interactive instead of just listening to me kind of drone on. And down in the bottom right, it says, say something nice. What I'd like for you to do is, if you have a second, tell me, what do you think the slope of this line represents? So we're looking at the slope of the line. Think about the units that we have here. And remember that a newton is also a kilogram meter per second squared. So when you do slope, you always take this unit divided by this unit. So what is it that this question mark, what is my slope represent? So what is my slope? Yeah, and Jack is right. Jack says it is the mass of the system, okay? And that's because this is really y is equal to m times x. So whatever we plot on the y, if it's force, and then whatever we plot on the x is acceleration, then I know that my slope is going to be the mass. Conversely, you could also change this, and instead of putting acceleration there, it's really easy to just put mass here. And if I put mass on the x-axis, then my slope will be my other variable. So now I would have the sum of the forces is equal to acceleration times mass. Because I've plotted force in newtons here and mass in kilograms, then what is it that I would have on my slope? So I'll let you answer again here if you have an idea. So what is it that is on the line? So what does the slope of the force versus mass graph give me? I'm going to give you about 5 more seconds to answer. Yeah, very good. So it would be acceleration. It would be acceleration. All right, so that is just a little bit of how to graph this one. Let's go ahead and take a look at energy. And I think before we do that, we had somebody ask about circular motion. So what I'd like to do is let's go ahead and go through some things with circular motion, but we'll just kind of maybe try to tie it to graphing a little bit. So, Albertson, you want to know about circular motion. I'm going to go over one thing, and then if you don't mind, if you can maybe type in the question spot, let me know exactly what you want to go through, and I'd be glad to do that. That'd be awesome. So let's go ahead and let's look at circular motion, okay? And let's look at graphing for circular motion, because if you can do a lot of the test, a lot of the AP test really is just looking at what's happening in terms of how we plot things to try to figure some other things out. So you've said acceleration, and I know that acceleration or centripetal acceleration on the AP physics equation sheet is equal to velocity squared over the radius. So let's just create a little problem here. Let's say that somebody is swinging something in a circle, or better yet, we're looking at looking from the top down, and there's a car and it is doing donuts. And so it's going in a circle like this. And we start to go through and we measure some things, okay? We watch the car do a donut like this, and then we watch the car do a really small donut. And then we watch the car do a really big donut. And then finally, we watch the car do a gigantic donut, okay? And then we do another really small one. So each of these have a different R value. So one of the R values, let's say that it's 1 meter. Let's say that this one is 3 meters. Let's say that this one is 5 meters. We'll do 7 meters. And let's say that this one is 15 meters, okay? So we've got 1, 2, 3, 4, 5 different R values. So I have 5 different R values. So those R values are, so let's put an R here. Those R values are 1, 3, 5, 7, and 15, okay? And then the other thing that we are going to notice here is, let's look at some velocities. So let's say that the velocities, okay, and what kind of velocity is this? Well, the velocity that we see here is what we call tangential velocity. So if I want the tangential velocity here, that would be v squared over r. So this is our tangential velocity. So it's tangent to the circle. And so let's just come up with some of those. So let's go ahead and call this, well, let's go 1, and then 2, and 3, and 4, and 5, and 6. So what I could do is I could go through and I could plot these. And when I plot them, I should end up with a curve. So it's going to look a lot like this, okay? And here I've got R, here I've got velocity. So if I want to make this a straight line, I need to square all these R's. And if I square all these R's, what I'm going to end up with is a straight line. And that straight line, let's say that the slope of the straight line is 15. And notice that if it's 15, well, you know what? Let's do this instead. Let's say that we plot it, and if we do V versus R, let's say that we actually come up, instead of that other curve that we got, let's say that we come up with a curve like this. So this is what we call a square root curve. So if I want to make this a straight line, I have to go through and I need to square everything that is on the y-axis. So I want to square all these things. And if I do that, I'm going to end up with a very nice straight line. And let's say that this one has a slope of 15, okay? So from this, notice that if I do the slope of velocity squared over the radius, I should get the acceleration. So this would be my acceleration. So this is v squared, and this is r. So here we're looking at velocity change in circular motion. So we're looking at how this velocity changes and how the radius changes. So we're changing the radius, and that's making the velocity bigger and bigger. So as you go from a small radius to a really big radius, our velocity gets really big very quickly. So we've got now 15, but we need to figure out what are the units. So this is a meter squared per second squared, and then this is a meter. So what would be if our slope is 15, okay, and that's a meter squared per second squared over a meter, what are my units for this line? So if I take a meter squared over a second squared and then divide that by a meter, notice that one of the meters crosses off and I'm left with a meter per second squared. So this straight line is my centripetal acceleration. So that is one of the things that you can do. So I see that Albertson has also asked about looking at the mass of an object in orbit. So I think what we'll do here is we're going to go back to energy, and we're going to take energy and circular motion, and we're really going to put them together. And so we're going to try to find the mass of an object that is in circular motion. So let's go ahead and try that. So let's make up a system here. Let's put, oh, I don't know, we've got a planet here, and then we've got a moon, and the moon is out here. All right. And I want to find the mass of that moon that is in orbit. And so we're going to use some small numbers, but recognize that these would be really big if we tried to do something else, okay? So we're going to look at it a couple different ways. There's two equations we can think about. We can say that the force due to gravity, or the gravitational force, is equal to big G times m1 times m2 all over r squared. So that is the gravitational force. We also could think about what is UG. So UG is big G, M1, M2, all over R. So this is the energy of an orbit. So energy of something going in an orbit. Let's also think about what acceleration is. So acceleration is equal to V squared all over R. And so let's put some numbers on this. Let's say that this planet has a mass of 5, and let's say that this moon, well, let's make it 50. And then this moon has a mass of 2. And they want us to go through and let's see if we can find out what the mass, well, you know what, let's leave this 2 off. Let's see if we can find this mass. So we're going to try to figure out what is the mass of the moon, okay? We need to add some things to this. So let's say that our tangential velocity is equal to, and let's just do something nice. So let's do 2,000 meters per second. Okay, so it's moving pretty quick. Let's say that the distance from here to here, or our value, is, oh, I don't know. Let's say that it is 5,000 meters. Okay. And oh, I don't know. I think that's probably really all we need. So let's go through and see what we can find. We're trying to find out what is the mass of this little guy right here. Okay. So we know that the energy is equal to big G, M1, M2 all over R, and we know the acceleration is equal to V squared over R. We also know that the force due to gravity is equal to G, M1, M2 all over R squared. What else do we know? Well, let's just try to plug some stuff in here. Notice that I have an R here and I have R here also, okay? So what we might do is we can try to solve for one of these and then see if we can find out what this mass is. So let's go through and do that. Let's first find out what our acceleration is. So let's find out what our acceleration is. So the acceleration here is equal to, and then we're going to put 2,000, and we're going to take that, square it, and then we're going to divide by 5,000. So 2,000 squared, if I do that, 2,000 times 2,000 gives me a really big number. And if I divide that by 5,000, I find out that my centripetal acceleration, so that is the acceleration that points toward the center, is approximately 800 meters per second squared. Okay, so that's our centripetal acceleration. So that's this guy right here. Can we find out what the force due to gravity is? Well, we also know that Fg, okay, so F little g is equal to, and that is the mass of something times the gravity. So now we've got all these equations. We're looking for, we know the mass of this one, okay? The question is, do we know the force between these two things? Do we know the force between these two things? Well, I know the centripetal acceleration, and that's the one that points towards this planet. And I know this, which is the mass, and so we're going to call it 50, and so it's not very big. So we're going to put m here as 50. And my question is this gravity equal to the centripetal force? Is gravity equal to the centripetal force? And so in actuality, we're going to have to be careful here because we don't want to make any assumptions that are incorrect. If you're standing on the Earth, is gravity equal to the centripetal force? And the answer is no, not really. So let's see if there's something else we can do with some of these. The big G here is 6.67 times 10 to the negative 11th, okay? And let's say that we find out that the force between them is pretty small. Let's say that it is let's say it's 3 times 10 to the, I don't know, let's do negative fifth. So if my big FG is 3 times 10 to the negative fifth, and that's equal to 6.67 times 10 to the negative 11th, if my mass of my first object is 50, and the mass of the second object is something that we're looking for, and we need to divide by the distance between them. And so the distance between them squared would be 5,000 squared. So now we want to solve for this variable, which is the mass of this moon that's going around the outside. So we're going to take 3 times 10 to the negative fifth, and we're going to multiply that times 5,000 and multiply times 5,000 again. And then we're going to divide by 6.67 times 10 to the negative 11th. And we get a really big number. And then we're going to divide that by 50. And we get 2.25. 2.25 times 10 to the 11th. So that is a very gigantic moon. In fact, we probably should have this circling the other one. All right, so that's just a little bit about centripetal. Probably the thing that we can do next is we're going to skip over momentum, and let's take a look at some physics problems that deal a little bit with circular motion. So this one kind of does, kind of doesn't. It's more of a pendulum. But we're going to go through, and this involves all kinds of really great physics. So one of the things it's going to deal with is dynamics. So on a final exam, I would give problems like this because this one's going to have several things in it. It has dynamics. It also has energy in it. So let's go ahead and go through and do this. So here we go. We have this string, and it is attached to another string. And they want us to draw a free body diagram showing and labeling the forces on the bob in the position shown above. So we're going to do that. We're going to go up to the left, and this is force of tension, and this is for the first string. And then if I start here and go over to the right, okay, this would be the force of tension, and we're going to call this string number 2. Okay, that's the horizontal string. Finally, we're going to move straight down, and this one is going to be equal to m times g. So now I've got everything that I need. The thing that you have to be careful of is when they say a free body diagram, I can't put any components in. So I have to be really, really careful about what I do. The next thing they want us to do here is find the tension in the horizontal string. So they want to know what is the tension in the string. So to do that, we're going to set up two sum of the forces equations. So here's one, and we're going to make this one in the x direction. So that's left to right. So this is going to be positive x. And then we're going to do one in the positive y direction. So this is going to be sum of the forces in the y direction. This one is equal to 0. And this one is also equal to 0. So why are the forces equal to 0? Well, the forces are equal to 0 because this is a static system. It's not moving and it's not accelerating. So let's go ahead and do all of the forces that we see in the x direction. The only problem is we need to draw another diagram. This diagram has ft2 in it, and this one's fine because it's in one of my two directions. mg is okay because it is in the y direction, but this ft1 is a problem, and it's because it's in both directions. So what I'd like to do is I'm going to go ahead and put in components. So here are my two components, and I'm going to go back up, and I see that the top of this is 30 degrees. So I'm going to put this in, and I'm going to put 30 degrees right there. And then this side of the triangle is going to be ft1 times the cosine of 30. So that's in the y direction. Notice how it's going up and down. And then this one right here is ft1 times the sine of 30 degrees. So it's the opposite side. So that one's really important. So let's go ahead and let's fill in what we know here. So in the x direction, we said to the right is positive. So we're going to put in ft2. So ft2 minus, this one is going to the left. Notice we're starting at the circle. We said it goes to the left, minus ft1 sine of 30 degrees. And that's equal to 0. So now we're going to just go ahead and solve for ft2. So ft2 is equal to ft1 sine of 30 degrees. Now let's do the same thing in the y direction. We said up is positive, so the only thing we have going up is ft1. So this is ft1 cosine of 30 degrees. And that is going up, so the one that's going down is mg. And that's equal to 0. So we're going to set these two things equal, since we can just add mg to the other side. So this is cosine of 30 degrees, and that is equal to m times g. All right, so now I have two equations, and I want to be able to find out what are the forces, okay, going just in the x direction. So I want to know what is ft2. So I want to know what is ft2. So I'm going to solve this one for ft1. And I'm going to do that because then I can plug in whatever I have into this spot, and that will tell me what ft2 actually is. So this is equal to, I'm going to divide both sides by the cosine of 30. So this is going to be mg over the cosine of 30 degrees. So now I know what ft1 is. I'm going to plug this guy in. So I'm going to go from here, and I'm going to plug it in for ft1 here. So let's make the new equation blue. So this is ft2 is equal to, now I don't have ft1 anymore. I've substituted this. This is mg times, mg over cosine of 30. And then on top, I have sine of 30. So if you remember your trig, you know that sine over cosine is tangent. So this is ft2 is equal to mg times the sine of 30 over the cosine of 30, which we said was tangent. So let's just go ahead and write tangent in here. So this is mg times the tangent of 30 degrees. Our mass that they gave us was 1.8, so I'm going to plug that in. And then a gravity, we can use 10, so that's common on the AP test. Go ahead and use 10, it makes it a lot easier. I'm going to take that times the tangent of 30 degrees. So here we go. We're going to do 18 times the tangent of 30 degrees, and I end up with a tension in string number 2 of 10.4 newtons. So just to review, we drew the free body diagram. We didn't draw anything else on it, Now we drew a diagram with components. We found the sum of the forces in the x and got this equation here. Then we found the sum of the forces in the y and found this one. And now I can substitute in, put my numbers in, and I found out that it's about 10.4 newtons. So the next thing they want us to do is they say the horizontal string is now close to the bob and the pendulum swings down. Calculate the speed of the bob at its lowest position. So if we think about our picture again, we're going to cut this string, and this guy right here is going to move in this direction. So it's going to move, and the highest speed is actually going to be at the bottom. So one of the things that we're going to do is let's go through and draw a diagram here again. But this is my pendulum, and then this is my pendulum when it's at the bottom. Okay. So notice that if I draw a line straight across here, and I want to know how far it fell, this is delta y. So that's the height that it fell, and it fell along the arc. We know that this is the length of the pendulum. From here all the way down to here is the same length, but then we have this little space here that we want to find. Well, we already know that this angle is 30. So let's do this. If we look, we see we have a triangle right here. I want to know what is this in terms of L. So to get this, I'm going to say it is L times the cosine of 30 degrees. So this one is L to L cosine of 30 degrees. Okay. So at this point, if I want to know what this little spot is here, I can take L and subtract L cosine of 30. So I take the whole thing, get rid of this, and that'll tell me what delta y is. So delta y is equal to L minus L cosine of 30 degrees. The other thing you could do is you could say it's L times 1 minus the cosine of 30 degrees. So that is my change in y. So why do we mention that? Well, here's why. Down at the very bottom, we have kinetic energy. And then up here, we have potential energy due to gravity. And I know I'm going from one to the other. So what we'll do is we're going to move back down here, and we're going to create what we call an LOL chart. So we have a couple of energies here. We know we have potential energy due to gravity and kinetic energy. And then we're going to put the same two here. And we know we start with all potential energy due to gravity because we are calling the bottom of this, so right here, our height or our position in the y is equal to 0. So let's go back, and that potential energy in our system, which includes the pendulum. So I'm going to put pendulum and the earth. Okay, those are the only two things we have to worry about. That all of the energy is converted to kinetic. So the string, we don't worry about any friction there. We don't worry about any of the energy being lost since there's no air resistance. So everything's going to go from energy that is potential and gravity to kinetic energy. So here's our equation we're going to use. We're going to say that UG is original is equal to kinetic energy final. We don't have any original kinetic. We don't have any final potential. So we're going to leave those out. This is equal to mg delta y. And then this is equal to 1/2 mv squared. Now, what's cool about this is mass doesn't matter. So we're actually going to get rid of the mass on both sides. They want us to figure out the speed of the bob at the lowest position. So we're looking for v. So let's solve for v. So if I solve for v, v is equal to, I need to multiply both sides by 2. So this is 2 times gravity times delta y. But then I have the square here. So I want to take the square root of both sides. And I end up with velocity is equal to 2 times gravity times the square root times the change in height. We said earlier that we can use 10 for g, and we also said that this is L minus L cosine of the angle, and that was our delta y. So what was L and what was our angle? So here we've got 2 times 10 times L. So let's go back up and we see that L was 2.3 meters. So we're going to put in 2.3 and we're going to factor that out. So that gives us 1 minus the cosine of the angle, which is 30 degrees. All right, so let's go ahead and do this math. So I'm going to take 1 minus the cosine of 30. That gives me 0.1339 or 0.134. I'm going to multiply that times 2.3 times 10, and then finally by 2. And I end up with 6.16, and I have to take the square root of that. And my answer here is 2.48 meters per second. And that is actually a tangential velocity. So we were talking a little bit about circular motion. And one of the things that we could do now is we could find out what is the centripetal acceleration of this thing. Okay. So we want to know, since we know what the radius is of the circle, it's 2.3, and we know the velocity, let's find out what is the centripetal acceleration if we ignore kind of what's going on with gravity here. So we could do v squared all over r. So this is 2.48 squared over my r, which we said was 2.3. And so now if I do 2.48 squared and then divide by 2.3, we end up with 2.67. So 2.67 meters per second squared. All right, so that is one AP problem that will help you a little bit. So that had both energy, we added some circular motion to it, and it also has dynamics in it, so drawing free body diagrams and things. Let's take a look at this one. Now, this is kind of difficult because when you look at this, there's a lot of different things in it. We're going to do this first part, and then I think we're going to be out of time. So we're going to try this. In an experiment, students are to calculate the spring constant K. So remember, springs have a constant, and that spring constant, if we use force, so the force of a spring is equal to K times X. So the K value tells me how strong a spring is. So this is the strength of the spring. It's measured in newtons per meter. So how strong it is, or how much it resists stretch or compression per unit length. This would be the compression or the extension, and then this will tell us what the force is. But there's another way to do this, and it's to use US, and that is the energy of a spring. That's equal to 1/2 kx squared, where this is still the strength and this is still the stretch, but we have to square it, okay? So they want us to find an expression for the height of this spring as it goes up in terms of m, x, k, and any fundamental constants. So let's kind of talk about what each of these things are. You'll see an h right here. This is the height that it jumps up. We could have also done it from the bottom of the spring up to the bottom of the spring. So this is also h. But here we see that it's been compressed. And so our compression here is x. So it has a compression of delta x. What kind of energy does it have here? So right here it has spring energy. And then up at the top here, we have converted that spring energy into all of it is now gravitational energy. So if we did an LOL for this, our system would be the spring, and it would be the Earth. We also have a table here, and so we're going to put the table on there because that's going to be important just for the fact that it launches off the table. Otherwise, it'd be floating. So we know that when we compress it, we have potential energy of the spring. We don't have any gravitational potential energy. Why? Because we're calling this right here 0. So that's 0 height. Or we could call this 0 height. Depends on which one of these H's you're going to use. So we don't have any potential energy due to gravity, but we do have spring energy here. Over on the other side, all of that spring energy is now potential energy due to gravity. So let's set up an equation. We have US is equal to UG, and we want to put everything in. So this is 1/2 K x squared is equal to mg, and then we have h. So we're going to put h in because it wants everything in terms of h, m, x, k, and fundamental constants, which includes our good friend gravity. So let's solve for h. H is going to be really easy here. We just divide both sides by mg. So this is going to be kx squared all over 2 times mg. So now we have our equation for the height. The next thing that they want us to do on this one is figure out what quantity should we graph so that the best fit line will be the spring constant K. So remember, a lot of the questions deal with graphing. So we're trying to figure out what are we going to put on our two axes to figure out exactly what the slope would give us to be K. So they told us that it's compressed a distance of 0.02 meters in each trial. That means that it doesn't change x at all, okay? So let's go back to that equation we had. H is equal to kx squared. So let's put it over on the side here, all over 2 mg. And so now what I want to do is look and say, okay, I want to find out if I have this equation, which of these things do I need to change to make it a straight line? So I know that x is staying the same each time. Okay, so it is compressed distance on each trial of the same thing. So we're going to cross it off for what we're going to do in terms of the graph. The other thing that stays the same is going to be gravity, and so does our number 2. So if I want to solve this again for K, so K is equal to H times M. Well, that doesn't do us much good. But if we say this is Y is equal to M times X, our M, okay, we want it to be K, so that's where this is. And I know that H is going to be my y-axis. So I'm going to put H there. And then this is really H is equal to K times 1 over M. So that's the same thing. So down on the bottom, I'm going to put 1 over M. So now if I plot H versus 1 over M, I'm going to get something that's going to help me find K. It's not exactly K, it's just approximately close to K, okay? So on this table, what I would have to do is I would have to do 1 over each one of these masses. So it'd be 1 over 0.02, 1 over 0.03, and then I do the same thing all the way down. Once I have that, I'd be able to plot it. But once I have my straight line, they want to know if what can I plot so that I can get the data points to use them to calculate the spring constant. So I want to play H versus 1 over M. Down at the very bottom of this, they want us to find the value of the spring constant. So let's say that we got this guy. We know we've plotted H versus 1 over M. And so they want to know, how do we find the spring constant? So let's go back to that original equation that we had. We said H is equal to kx squared over 2mg. So this is kx squared over 2mg. And we know that the slope here is h divided by 1 over m. If I take h over 1 over m, and I want to simplify this, I can multiply both the top and the bottom by m over 1. And if I do that, the m's cross off, and now I end up with m times the height. So let's set this equation equal to k. So k here is equal to 2mgh all over x squared. If I know that 2 is constant, m times h is now a constant, so that's a number. So now this is equal to 2 times m times h, that's my slope, times gravity, and then we're going to divide that by x squared. So now I could plug all of my numbers in, and that would give me an actual value for our height. No, actually for the k value. So there's a lot to a lot of these. I think the best thing to do is go through whatever your teacher has for you in terms of your review. But this kind of shows you what you can expect on the AP Physics test. And so a lot of the final exams will have problems actually from those. Okay, cool. So other than that, I think that is the end of the stream. I appreciate you coming out and taking a look. There's some other streams that you can take a look at. So that is 100% all up to you. And that is it. I will let you go. Thanks so much for showing up for this Fiveable review.